I'm really delighted to talk to you on one of my favorite topics, California's water, energy, climate nexus. Next slide, please. For those not familiar with the Pacific Institute is an independent nonprofit organization. We were founded here in the Bay Area about 35 years ago. And now have staff around the world. Our mission is to create and advance solutions to the world's most pressing water challenges. And the topic of water, energy, and climate has been really a focus for us for over 20 years. I'm excited to talk to you more about that today. Next slide, please. Today, I'll talk a little bit about California's water energy nexus. I'll then describe some of the emerging water and energy trends. And then finally, describe some of the implications, of the water energy nexus and those emerging trends. Next, please. And go ahead and go to the next. Let's first talk about the water energy nexus. This is really a simple diagram for a very complex topic, as Ryan really pointed out. And there's really two sides. On the one hand, looking at the water for energy, and energy for water. I think for most people, if we say water energy, the first thing they think about is hydropower. And of course, hydropower, in that sense, we're using water to generate energy and electricity in that instance. But we also use water across the energy fuel cycle. So we're using water to extract for fuel production, whether that be ethanol or hydrogen. We're using water to extract and refine for mining, for example. And we're using water to cool thermoelectric power plants. We're using it to wash solar panels. So there's quite a bit of water use across that energy fuel cycle. And we also are using energy for water, for extracting water, pumping groundwater up to the surface, moving water from its source, conveying that water to a treatment facility. We're then using energy at the treatment facility, then to distribute the water to households and businesses. We're using water inside homes and businesses mostly for heating, sometimes for pumping if it's in a high-rise building. And of course, we're using energy again for wastewater treatment. So next slide. I'll focus today on the latter half of this, on the energy for water piece. And as you will see on the next slide, in California, it's estimated that about 20% of the state's electricity and a third of our natural gas usage is water related. Again, that's water we're using to capture, treat, to heat, pump, treat wastewater. And, as we heard at the beginning, even in the Bay Area, relatively small area, there's quite a bit of diversity in where we're sourcing water from and the energy intensity of that. There's quite a bit for our imported supplies. Some of those are gravity fed, not requiring a lot of energy. Some of those, as we heard in Santa Clara, do require perhaps a lot of energy for importing into the region. But I think importantly, what I want to highlight, and you can see it, frankly, on both sides of this, the end use part of our water cycle here is where the majority of energy is used and consumed. Again, and when I say end use, I'm referring to energy use inside homes, businesses, institutions. Again, mostly for water heating, sometimes for other purposes as well. So even in a place that's reliant on gravity fed water, maybe doesn't have a lot of energy associated on the water supply side, still significant amount of energy use associated with end use, and in some instances wastewater treatment. So the topic of water and energy, and the topic of the energy embedded in water and the energy associated with water use is a topic for all of us, even in those areas where it may be gravity fed. Next slide, please. So now I'll touch a little bit on some of the emerging water and energy trends and what that means for the water energy nexus in California. This figure is showing the San Francisco Bay Area, population, We see total water use here in the blue bars. We also see per capita usage shown there in orange. There's a widespread misconception that as our population and economy grow, we use more water. But in fact, water use in the Bay Area, as shown in this slide, really peaked in the early 2000s. And we now use less water than in the 1980s, despite continued population and economic growth. This decoupling of water use and growth is due to a variety of things, including the uptake of water efficient devices, the installation of more climate appropriate landscapes, denser developments, and of course, changes in our economy from a more manufacturing oriented to a more service oriented economy. So these have been really, I think, important trends. And as you'll see on the next slide, there are a number of sort of policies, water efficiency policies at the state level that will continue to drive reductions in per capita use and even total water usage. On the one hand, I think a topic for which you are all very familiar, standards and codes for new appliances and fixtures. California has among the strongest standards for appliances and fixtures in the US, exceeding the federal standards pretty dramatically. We also have, as was mentioned, the Model Water Efficient Landscape Ordinance that limits grass for new developments and major redevelopments. Most recently, there is now a ban on irrigating non-functional turf with potable water that will go into effect starting in 2027. And then finally, regulations around making conservation a California way of life, which are regulations that are advancing. There's a sort of a rulemaking process happening now, but it would establish water budgets for urban water suppliers. So all of these things together will ensure that new developments are very efficient and will also support even efficiency in our existing developments as well. Next slide. We are also seeing in the Bay Area and in many areas a drive for developing new water sources. So even as we're seeing demands go down, we are also seeing greater variability and uncertainty with our existing water sources. And so there is interest and a lot of work happening to start to develop new supplies. This figure is showing the energy requirements for new water sources, ranging everything from desalinated seawater, as you'll see at the top, among the most energy intensive, all the way towards some of those local imports that we talked about, some of those gravity fed systems that are use very little energy. The units here are sort of kilowatt hours per acre feet. And what you will see, I've circled some of where I see the most interest, at least in new sources. And some of these are relatively high, some of them are relatively low. There's quite a bit of variability here. And the impact for any community will really depend on what it is they are currently using. So, great introduction, as we heard in Santa Clara, they see recycled water as being less energy intensive than their imported water. Other places, recycled water may be more energy intensive if it's an area that's currently dependent on gravity fed flows. So a lot of variability in terms of the impacts of some of these new sources. Next slide, please. So we've talked a little bit about some of the water trends. We have a growing population. We're seeing, though, declining usage, per capita uses, but a shift towards these more local sources with varying energy intensities. There are also some emerging energy trends I'm sure many of you are aware of. There is a major effort to decarbonize our electricity grid, also to electrify various end uses, including water heaters. So, if you're looking at these trends, some of these things would suggest that energy use would go down. Some of them suggest they might go up. And so there's really a lot of uncertainty about the combined effect of these trends on both energy use and greenhouse gas emissions. Next slide. Just in 2 years ago, Pacific Institute partnered with Next 10, which is a California-based energy nonprofit, to better understand the impact of these trends. The goal of our study was to estimate the energy and greenhouse gas footprint of California's urban and agricultural water sectors under various future water demand and supply scenarios. And I'll show you some of what we found. Next slide, please. I'm going to focus in on the urban. As I mentioned, we looked at both urban and agricultural water use and the related energy and greenhouse gas emissions. But while agriculture uses about 4 times as much water as urban areas in California, urban water is 9 times more energy intensive and produces 9 times more greenhouse gas emissions. So while the study that we looked at included agriculture, I'm going to focus in on the urban results because of that, but also because I think most of you, that's kind of the space you're all working in. In our study, we evaluated 3 scenarios for future water scenarios, both supply and demand. On the left side, we looked at a scenario of increased per capita water usage. For this, we relied on forecasts produced by water suppliers and their urban water management plans. And as we added those up for across the state, we also looked at their supply portfolios. What we found was that suppliers were projecting a significant increase in per capita water use going out to 2035. The net effect of that was a 44% increase in water use between 2015 and 2035. That would then result in more than a 40% increase in both electricity use and natural gas use associated with that water. And even despite the efforts to electrify end uses, to decarbonize the grid, those would essentially be offset by the increase in water use and energy use, such that greenhouse gas emissions go up under that scenario. Contrast that with, on the right, one of the scenarios we looked at was declining per capita water use. For this, we maintained sort of the 15-year statewide trend of reductions in per capita usage. And in this case, we saw that total water use declined by 17% despite continued population and growth. And this resulted in a reduction in water-related electricity and natural gas usage. And we found that the urban efficiency, coupled with decarbonization of the grid and electrification of end uses, could reduce water-related greenhouse gas emissions by more than 40%. So we concluded that decarbonization coupled with greater electrification of water heaters is important for reducing water-related greenhouse gas emissions, but that urban efficiency really offers that greatest reduction. It's sort of the helps us to realize really our not only our water goals, but our energy and our climate goals much more quickly. Next slide, please. I want to talk, so I talked a little bit about sort of the water energy nexus and what it means sort of at a statewide level, how it can help us to meet our energy and climate goals. I also want to talk about it on an individual device level, what it can mean for a household. And I want to highlight that the energy savings really help to make water efficiency measures more cost effective. The example I'm showing here is with a clothes washer. We have a new conventional clothes washer, costs about $450. Front-loading clothes washer, which is more water and energy efficient, costs a bit more, $750. If we looked at the water reductions associated with that, they estimate they save quite a bit of water with the front-loading clothes washers. Still, if we were only thinking about the water cost, we would still see that front-loading clothes washer was more expensive over its lifetime than a more conventional top-loading clothes washer. Next slide. But as you'll see, when we pull in the energy costs over the lifetime of the device, we start to see where the front-loading clothes washer is very cost-effective. In this instance, if you look annual lifetime, it's about $1,200 for the front-loading clothes washer compared to more than $1,300 for the front-loader. So higher upfront cost, of course, but those are more than made up through lower water and energy costs over the lifetime. So that, again, it highlights, I think, the importance of this water energy nexus, not only at the state level, but also at the individual level as well. Next slide, please. We also find that energy savings from water efficiency are cost competitive with other energy efficiency programs. These are slides that came from a study out of UC Davis. This study looked at the drought, the 2012 to 2016 drought that we had in California when then Governor Brown asked for a 25% reduction in urban water use. And what this study found is shown there on the left, that the energy savings from the conservation that we achieved as a result of that call exceeded the energy efficient, all of this energy savings from the energy efficiency programs developed by the investor-owned utilities for that year. So the water conservation mandate and the resulting reductions in demand were a significant contributor to energy savings. And importantly, at a time, of course, when we're in a drought, we know there's less hydropower. We tend to have far more pressures on our energy system as a result. And so this is an opportunity, again, for a win-win, right? Where we're addressing both water and energy challenges together and helping to meet those near-term goals, but also some of our long-term goals. As shown on the right, I also want to highlight a couple of other things this study found. The study looked at the cost effectiveness of these water conservation measures compared to some of the energy efficiency programs. And really what they found, it depended somewhat on the lifetime, how long they assumed these savings lasted. But even under assumptions of a 1-year savings from these water conservation, they found that they were quite cost competitive with the energy efficiency programs they were doing. So again, here we can see where water efficiency can help energy utilities also meet their goals much more cost effectively and benefit customers. Next slide, please. So I'll just kind of provide some of the key takeaways. We see that water and energy sources are interdependent resources and both really face constraints. Urban water efficiency is essential for meeting not only our water goals, but also our energy and our climate goals in California. Importantly, energy savings can make many water efficiency measures more cost effective. And finally, we find that energy savings from water efficiency are cost competitive with other energy efficiency programs. Next slide, please. If you're interested in learning a bit more about some of our work on the water energy nexus, I would encourage you to look on our website. All of our publications are listed. They're no cost, but we love people to download them. One of the ones I wanted to highlight as well is shown on the left. I apologize, it's not the best picture, but in 2022, we also worked with the California Public Utility Commission. They have a water energy calculator that they use to really help energy utilities quantify the embedded energy savings associated with their water efficiency investments. It's a tool that allows them to better estimate those savings. We also, though, work such that energy utilities are able to get credit for those water-related energy savings towards their energy goals. So, if you're interested in learning more, that's also listed on the California Public Utility Commission's website, and I'll put a link when I'm done talking to where you can find that as well. So with that, I'd like to thank you for your time and hand it back over. Thank you.